All right, welcome. So today's session will be on something that I find very exciting. So we're going to talk about non-measurable sets and the axiom of choice. And it's going to be weird, so brace yourselves. OK. When I was a kid, there was a little math puzzle that we kids like to tell each other. And maybe some of you guys have heard about it. So the idea is you have these people lined up. Maybe there are 10 people. And the person on the back can see everyone ahead of her. And then the next person can see everyone ahead of him, and so forth. At some point, everyone has closed their eyes. And an assistant has approached each of them and flipped a coin. And depending on the outcome of the coin toss, they were given a red or a blue hat. So the idea is everyone can see the colors of the hats of people in front of them, but not the color of their own hat or the hat behind them. And then, like, something terrible is going to happen. Going from back to front, each of them is going to be asked about the color of their hat. And if they say the right color, their life will be spared. If not, they'll be shot. And then the puzzle is to find a way of minimizing the people killed by having the group agree on a strategy beforehand. So has anyone heard about that puzzle? Oh, yes. I mean, yeah, do you want to say these?
I don't actually remember how to do it, but does this have something to do with the dragon puzzle? Because I
don't know the dragon puzzle.
Oh, okay. Because I think I've done something similar, but it might be a little different, with a bunch of dragons who are all blind and they're either green or red scales.
Oh, it could be.
And something like that, but I don't really remember actually.
Okay, so the answer that do you want to? Yeah. Right. Yes.
I don't know if anyone else has it as the 100 gnomes, but it's the idea that you can have the last person in the back sacrifice themselves so that everyone else survives. And by sacrifice, I mean there's a 50-50 chance they'll survive. So it's a counting problem. It's the idea that if you count up all the amount of reds and blues in front of them, he shouts out which is, I think, more, I believe. And he'll either survive or not, because that depends on the majority or the minority. It could be either or. But the person in front of them can then count up, like in a binary way, which is how many reds and how many blues there are. And then based off of that and the answer before them, they can figure out whether or not they're blue or red. And then they call out what they are and then moves forward, and same concept, so on and so forth, all the way to the front.
Right. This is what we use. It certainly had that flavor, but the idea was that you just said whether you could see an odd or even number of, say, red hats. And then the crucial thing is that the person could use the combination of what you said and what they could see to figure out the color of their own hat. And then everybody else could use not just the original thing, but also what the next person said and the next person said, and so forth. So you wanted to say something about it. What was that? Yeah? You were just nodding. It's OK.
Well, I guess I could mention that it works for n colors. You say it in base and your mod, and so everyone choose so you choose, you correspond like 0 to n-1 with the colors.
Oh, I see. Cool. That had not occurred to me. Cool. OK. All right. So I thought that was a cute puzzle and didn't think much of it. But then one of my students told me about the mother of all hat puzzles. And that is the puzzle I want to talk about today. OK. So the mother of all hat puzzles involves not finitely many people, but infinitely many people. So you have 0 looking that way at the very back, and then 1, and then 2, and 3, and so forth. So 0 can see the color of everyone's hats except for her own, and 1 can see the color of everyone's hats except for 0 and 1, and so forth. And much of the setup is similar. So at some point, everyone closes their eyes, and each person gets their own assistant. Each person's assistant flips a coin and uses the outcome of the coin toss to decide what color hat to give them. And then at some point, they all have to say the color they think their hat has, and they'll get shot depending on what happens. But at this point, some differences take place. So the first and most important difference is that in the finite version of the case, people said the colors sequentially. So the idea is that you can use information about what people behind you said to make your decision. In this case, that's not going to happen. So they're all going to have to answer at once. Or equivalently, they could just all whisper it to their assistant. Here's what's amazing about this case. There exists a strategy that people can agree upon in advance, much like in the other case, which guarantees that at most, finally, many people will die. So it guarantees that almost everyone will survive. And yes, you look puzzled, and rightly so. It seems impossible. It seems impossible because, look, for the baby case that I told you guys about, you have some information that helps you. So it's true that you don't know the color of your hat, but you can see the color of the hats of people in front of you. And you can use what people behind you have said as an encoded message about how to extract the color of your own hat from what you can see. But in this case, there's no message. In this case, all you have to go on is the colors of the hats of people in front of you. And by the definition of the case, the decisions about what hats to place on people were independent of one another, because each person got their own assistant with a coin toss. So the hat decisions were all independent of one another. So it seems impossible, and yet it's true. In fact, it's worse than true. So often with these puzzles, like, it all seems very mysterious, and then you hear the answer and you say, okay, it's not so mysterious. But this is not like that. So I'm going to tell you guys how to do it, and you'll see how it's going to be worse rather than better. So like, knowing how to do it is only going to make it seem more puzzling. So yeah, do you?
Or like the solution to it?
Oh, you can. I mean, if you have thoughts, I want to hear them.
Or, well, later.
Okay. I mean, this is hard. So I don't think one can expect anyone who hasn't heard it before to just say, I know how to do it. And also, like, it doesn't matter, because I think that what's truly difficult here is just like knowing what to do with the result once we have it, as opposed to coming up with the result. Okay, so here's how to do it. So think of each point in this space as a possible sequence of hat colors. So I'm just going to think of one color as 1 and the other color of 0. So you can think of each point here as just a sequence of 0s and 1s, indicating one possible distribution. And what I'm going to do is I'm going to divide up this space. According to a particular equivalence relation. So I'm going to put two sequences in the same cell, just in case they disagree only finitely. So for example, I'm going to put 0, 0, 0, 0, 0, 0 in the same cell as 1, 1, 1, and then all zeros, because they only disagree in their first three positions. They agree everywhere else. But I'm going to put either of those in a different cell as the sequence that just alternates ones and zeros forever, because these guys are going to disagree in all odd positions, and these guys are going to disagree in almost all odd positions, and therefore infinitely often. So all we have so far is a classification of possible sequences. So here is the strategy that our group of people can agree upon in advance. What they can do, and of course this is going to require them having superhuman powers. I mean, not unlike the power to see infinitely many hats in front of you. They are going to decide on a representative for each cell. So they're going to, as it were, they're going to name a captain. From each cell. And then the strategy is super, super, super simple. What's going to happen is that people are going to open their eyes, and they're going to be able to see almost all of the sequence. So for example, suppose that this guy says, well, I don't know what zeros hat is like, so I'm just going to write a blank, and I don't know about one blank, I don't know about my own blank. But from that point on, I know what the sequence is. Now notice that even though these three values are missing, and therefore 2 does not have enough information to determine what the actual hat distribution is, 2 does have enough information to determine which cell the actual sequence lives in. Because look, something 2 could do is just make up some values. So say just assume that those 3 are 1s, and then go to the corresponding cell, go to the cell where that sequence lives, and then because the actual sequence will disagree at most in 3 positions from this one with the made-up 1s. So it's got to be in the same cell, because you put sequences to the same cell if they disagree only finitely. So everyone opens their eyes, and everyone knows what cell is the right one. And their strategy is just guess on the assumption that the actual sequence is the previously agreed upon representative for that cell. So you go to the cell where you know you are, and everyone had agreed on a representative from the start, on a captain for that cell. So they all agree that they're all going to answer on the assumption that that is correct. So what's going to happen? Well, this is what we know. We know that they're choosing accordance with a representative, and we know that the representative and the actual sequence are in the same cell. So we know that the representative and the actual sequence disagree only finitely. So if everyone chooses in accordance with the representative, only finitely many people are going to get it wrong, because there are only finitely many spots where the two sequences disagree. So at most, finitely many people are going to get shot. Okay, now you see what I mean. Like we're in a worse situation now than we were before. And I mean, let me just say something to bring out just how horrible our situation is. So you might have thought that if they had agreed on no strategy and people just guessed the color of their hat, then the probability of guessing correctly would have been 50% because it was decided by a coin toss. But it seems like in using this strategy, nobody has access to any additional relevant information. So it would be different if instead of using this method, like they decided to use the method of like bringing out a mirror and like looking at the color of the hat, that would definitely increase the probability of their guessing correctly. But because they acquire no additional information, it is just totally unclear how one could raise the probability of guessing correctly beyond 50%. And if they don't, how could they possibly guarantee that most people are going to be saved? All but a tiny fragment. So of the infinitely many people, all but a finite number are going to be saved. Guaranteed. So what's going on?
So I don't know actually like how to compute the probability or whether it's more than 50%, but I do know that under the original case of just guessing for 50%, there is a chance that every single person will die, but this clearly guarantees that some people are going to live. So at least under that assumption, for the whole group, it's more optimal than just everybody guessing, even if it's not more optimal for like certain individual people. And also, like, even though a huge number of people are going to die, since the total number of people is infinity, like, it's still like a small fraction, if that makes sense. So
Tiny fraction. It's a tiny fraction.
Infinitesimally small, like, because it's infinite. So like.
So I basically agree with the different points you made. So one point you made is that even if people guess at random, there's some chance that they'll all guess correctly. And yeah, that's that. Or some chance they're going to guess wrong. So that's right. So what's surprising about this case is that there'd be a guarantee that, like, as long as everyone respects the strategy, they guarantee that most people are gonna be saved. You want to? Yeah.
I have a question. Can you say something about how logical space is divided? Like, how many cells are there? Yeah.
Okay. So I can say something about that. We will be better equipped to understand my answer to Rosa's question next week when we start talking about different sizes of infinity. But I can say it anyway, and then don't worry if it seems mysterious. So we're going to see next time that not all infinities have the same size. So the smallest of all infinities is the infinity of the natural numbers. So this is a very small infinity. And a bigger infinity is the infinity of the real numbers, or indeed even just of a segment like 0, 1. So the answer to Rosa's question is that within each cell, there are going to be as many sequences as natural numbers, so a small infinity. But the number of cells is going to be very large. So the number of cells is going to be like the number of points in here. And actually, that turns out to be important for some things. And maybe we'll talk about some of those things a little bit later. But well, that's how things stand.
So you are assuming the axiom of choice in order to make this map the function.
Yes, I am. That is absolutely crucial. So let me explain. The crucial assumption that I made is that it's possible to pick the representatives. My first reaction when I heard that that was controversial was disbelief. I said, well, what do you mean? Like, all the cells are there, and they're each filled with members. So just pick one. I think that people agree that that seems right, but mathematicians have discovered slowly and painfully that that assumption, the assumption that whenever you have a set of non-empty sets, there is a choice function for that set. That is a function that takes each of the members of your set and outputs a member of that set. So maybe I'll write it down. So suppose that you have a set, each of whose members is a non-empty set. Choice function for that set is a function that takes each of the members and assigns it some member of it. So it might assign A to A and B, and in the case of B, it's going to assign B, and maybe in the case of Z pi 2, it's going to assign pi. That's a choice function. So what the axiom of choice says is that whenever you have a set of that kind, the choice function exists. And of course, that is the assumption we use here, because you can think of each cell as one of the non-empty sets inside our set. And the choice of representatives is, in effect, a choice function for that set. What mathematicians have discovered is that, natural as that seems, it leads to very weird results. Maybe the most famous result, and you'll go after that, is something that I haven't decided yet, but we might prove it on Wednesday. It's the Banach-Tarski theorem that shows that there is a way of taking a solid ball that has, say, a radius of 1 meter and divide it into a finite number of pieces. And then take the pieces and move them around, but there's no stretching, there's no shrinking, there's no deforming. All you do is move them around and then reassemble them. And you get 2 balls with a radius of 1 meter. And like that boggles the mind. It's not obvious how you could get that from the axiom of choice, but if we prove it on Wednesday, you guys will see. So Saul is right. So it's clear that something weird has happened, and I think he's right to think that the axiom of choice is essential to generating that weirdness. But I feel like we still have our puzzle. So we still don't know what to say. Here's a question for you guys. So suppose that, okay, so here you have person K. Suppose person K was interviewed before the big decision, and they were asked, so are you worried? And K said, no, I'm not worried because, only finitely many people are going to die. And, I'm part of an infinite group. So it's just this, tiny fraction of the people who are going to get killed. It's very unlikely that I'm going to get killed. Would K be reasoning correctly? Okay, so it was at the same time, but you have not spoken, so I think it should be your turn.
Can we assume there's a world where there are infinitely many people?
Sorry, can we assume that there are infinitely many people? Well, it's true that that might be physically problematic, but I think that it's fine given the purposes for which the problem has been set up. So really what we want to understand is something about the nature of probability. So we want to understand how you can go from a situation in which you had at best a 50% chance of answering correctly to a situation in which infinitely many people are guaranteed to be saved, and at most finally many people can die. And you know, just for the purpose of illustrating that, I think is legitimate. Though I think your question is a good question. I don't want to be too cavalier about my answer. So I think that if you look at the history of our thinking about infinity, what's happened is that we just start out with all sorts of absurd consequences of working with infinities. And what mathematicians and philosophers have tried to do is to tame infinity, as it were, to come up with principles that allow one to work with infinity and not end up with absurd situations. And you know, maybe one conclusion that one ought to reach is that you know, this is not the kind of situation that we can deal with sensibly. Here, in fact, I'm optimistic. So my own view is that you know, there's some weirdness, but we can do good work here. But I think when we're working with infinity, that is always a good question to ask, like whether we've gone too far. Okay, you had a question, or is it?
I have a comment about person K.
Okay.
I think that the probability that person K will die is 0.
Okay.
Because I think that the limit of the probability as the number of people approaches infinity is equal to 0.
I agree that that is an argument. And it's hard for me to put my finger on something I don't like. But let me mention another argument that also seems plausible to me. So here's what was going to happen. We've, in effect, proved that there's going to be a certain point after which everyone's going to survive. So the point could be here, or it could be here, or it could be there, or it could be there. There are infinitely many places it could be. Oh. And of all those infinitely many places it could be, K should only get comfort from a finite number. So for most places where the cutoff point could be, that's no use to K. So I'm not poking a hole in your argument. I'm just saying that one of the weird things about this situation is that it seems like we get pressure from both directions. Okay, so here's what I propose to do. I'm going to bracket this for a moment, and I'm going to talk about non-measurable sets, and then I'm going to try to use the outcome of that discussion to come back to this problem and try to say something. My guess is that you will be unsatisfied about my conclusion, but I think that that is the best that the field has been able to produce. So, okay. So suppose that we're doing this. Suppose that we have the segment 0, 1, so the set of real numbers greater or equal to 0 and smaller or equal to 1. And we want to describe a mechanism for picking one of those points at random. Can anyone describe a method that someone could use? I mean, in principle and idealizing about what can actually be done in practice. Can anyone think about a method to do it? So a hint is that you might use, oh, okay, you have a proposal.
Does it need to be in finite time? Or?
Try it with infinite time, and we'll see what happens.
You can express it as like a decimal number, and for in binary as like a binary.
I like it already. Okay, so sorry, I'm going to interrupt just to explain that, and then you will continue. Okay, so that's right. So for any number in there, you can express it as an infinite sequence of zeros and ones following 0 point. So a 1 there means 1/2, a 1 there means 1/4, an 1/8, and so forth. So for example, 1/2 using this notation would just be 0.1. And something that's very easy to verify is that every number in here has an expression using this notation. In fact, there are some members in there that have 2 different expressions using this notation. Can anyone give an example? So 1/2 is, yeah.
Actually, yeah.
Oh God.
1/2 should.
Good. So that's one way of expressing 1/2 with this notation. What's the other?
0.0111.
Exactly right. And the reason is that 1/4 plus 1/8 plus 1/16 and so forth is just 1/2. OK, so sorry, that was just glossing your first remark. Go on.
And then you can go through each index and flip a coin for either a 0 or 1 in those situations to get a real number.
I love it. I love it. So just infinitely many coin tosses. Each toss is going to decide whether a particular position gets a 0 or a 1. I think that's great. There's a geometrical way of thinking of this, which is equivalent. So you could just take the 0, 1 line segment, and then use the first coin toss to decide whether the point you're going to pick is going to be the left half or the right half. And then say that you choose the left half. And then use the next coin toss to decide whether you're going to pick the left half or the right half of what you're left with. Say it's going to be the right half, and so forth. OK, so we have a cool method for picking a point on the line. Now, a nice feature of this method is that if you take the line and choose a segment of length L, then you could prove the probability that the selected point will be in L is L. So for example, if you ask, OK, so what's the probability that you'll pick a point which is between the 1/2 point and the 1/4 point? The answer will be 1/4. And special case of that result will be in this week's problem set. OK, so here is a question that one might ask. One might ask, is it the case that for an arbitrary subset of points on the line, an arbitrary subset of points in here, there is a well-defined fact of the matter about the probability that you will pick a point in that set? So we've looked at some special cases, and we know that in that case the answer is yes. So if you just pick a segment in here with a certain length, then the answer is yes, and the probability is equal to that length. There are other cases which are weird, but I think ultimately fine. So suppose that you just pick one point, say R, and you ask, what's the probability that our method will yield exactly R? Well, that will be equal to the probability that your infinite sequence of coin tosses will be one particular way, or in the special case in which you have 2 notations for a single number, one of 2 ways. And that is an event of probability 0. So the probability that you'll pick any particular number is 0. But that is not to be confused with the claim that it's impossible to pick that number. So probability 0 just means that it's so unlikely that any positive real number is too big to measure the likelihood that it's going to be that. So we have a situation in which for any point, the probability that it'll be that point is 0, but of course it's guaranteed to happen that some point will be picked. So, you know, it sounds weird at first, but I think that is like a perfectly respectable way of modeling the situation. Unfortunately, it turns out that there are some subsets of this line for which it's impossible to assign a probability. And what I'm going to do is I'm going to give you an example of one such set. So those sets are called non-measurable. And what that means is that it's impossible to assign them measure satisfying certain constraints. And you can think of a measure as a way of talking about the proportion of points that are in the given set. So if someone asks, what's the measure of L? You can read that as asking, what's the proportion of points on the line that is also in L? So the existence of non-measurable sets can be thought of as the observation that sometimes when you pick a subset of the line segment, there is no fact of the matter about what proportion of points are in your set. Okay. So the construction that I'm going to tell you about is due to Vitali, an Italian mathematician. So some of you might have heard the proof. It's very simple. And the example of a non-measurable set is usually called Vitali set. So here's how to build a Vitali set. And you will notice some similarities with the construction that we use for the hat puzzle. So start with the space of all points in the 0, 1 segment. And partition them into cells. In this case, though, the rule is going to be a little bit different. So we want to say A and B in same cell if and only if A minus B is a rational number. So a number of the form A over B for, well, n over n with n and m integers and m non-zero. So for example, there's going to be a cell in here containing 1/2. And that cell is also going to contain 1/8, because the difference between 1/2 and 1/8 is a rational number. But that cell is not going to contain, for example, pi minus 3, because the difference between that and any rational number is not a rational number. So we have these cells. Here's one way of thinking about these cells. So take the 0, 1 segment and then loop it around. So you have a circle of circumference 1. Then a cell like that one is going to consist of a bunch of points on the line, which is going to translate into a bunch of points in the circle, the rational points. You can get from the points in any one cell to the points on any other cell by applying a certain rotation to this circle. OK. So we have our cells, and so far nothing suspicious has happened. But now we apply the axiom of choice. As before, we apply the axiom of choice to pick a representative from each cell. I like to think of it as like a center for each cell. And the vitality set is just the set of all those centers. So it's just the set of representatives. And we're done. That set is provably non-measurable. And I'm going to tell you why. So to try and get a sense of what that set is like, again, go back to the version of the interval which has been looped into a circle. So the set of centers is all around the circle. And think about what happens if you rotate the circle not by any amount, but by some rational amount. That is the equivalent of picking a different center. So suppose, for example, that you had originally picked 1/2 of the center of that cell, and you rotate the circle by 1/4. Then you could think of that as picking 3/4 as your new center for that cell, and as picking as a center for every other cell, the member of that cell that is 1/4 away. And you know it's going to be there because we constructed the cells by putting together numbers that differed by a rational amount. So this is the result one gets. The result one gets is that if you start with a vitality set and shift it by a rational amount, you get another set which is just like the vitality set. They're just rotations of one another. And it's very easy to show that if you look at all rotations by a rational number, that covers all points on that circle. So for every point on the circle, it's either going to be in the vitality set or it's going to be in some rational rotation of the vitality set. So it's like having the vitality set and its siblings. You can break up the circle into a bunch of subsets which are just rotations of one another, clones. And therefore, you can break up the circle into a bunch of sets that should have the same probability as one another, because they're all clones of each other. And if you were to define a notion of probability that assigns different probabilities to clones, then you've changed the subject. So we have infinitely many clones, and they all need to be assigned the same probability. So what probability is it going to be? It can't be a probability greater than 0, because then if you added them together, you would get an infinite amount. And then you would have to say that the probability of the entire circle is infinite. And it's not. The probability of getting a point in the circle is 100%, i.e. 1. And if you instead chose 0, then you would have to say that the probability of picking a point in a circle is 0, because the result of adding 0 plus 0 plus 0 plus 0 is just 0. So it can't be something bigger than 0. It can't be 0. So there's nothing it can be. OK, so let me just summarize. If people want to go back to the proof of this result, it's in the lecture notes, which are linked to the course website. But let me just summarize what's happened. So we've taken the 0, 1 interval, and we've identified a particular subset of that interval, V. And we've shown that V has a number of clones. It has infinitely many clones. And that the clones, in effect, form a partition of 0, 1. So every point in 0, 1 is in exactly one member of the clone. But we want all the clones to have the same probability, which means that there's no probability that will fit, because 0 is too small, and numbers above 0 are too big. Damien.
I just want to say, crucially, there's countably many.
Yes, that is a good point. So what I'm going to do is I'm going to open a parenthesis. Don't worry if you have no idea what's going on in that parenthesis, but Damien is right, it's important, so if you follow, then that's fine. So one thing that we have not proved is that the number of Vitali clones is a small infinity. It's the infinity of the natural numbers. And as we discussed last time, there's an important principle of probability theory that says that when you have an infinity of that size, you ought to have the principle that says that if you have a partition consisting of that many members, then the probability that you'll get some point or other in some member of the partition equals the probability of getting a member of the first partition plus the probability of getting a member of the second partition, and so forth. So we use a version of that principle in proving that no assignment of probabilities to the Vitali clones could do. The reason this is tricky is because I earlier noted that the probability of getting any particular member of the line is 0. So there we have a failure of additivity, because you might say, well, look, if we're really going for this additivity constraint, then it ought to be the case that the probability of getting some point of the line equals the probability of getting that one plus the probability of getting that one plus the probability of getting that one. But those are all 0. So the probability of getting some member of the line should be 0. So in effect, what our landscape presupposes is that we should accept countable additivity, but reject additivity for bigger infinites. OK, so I close my parenthesis. That's actually a fascinating discussion, and I would love to talk about it, but things get tricky. So the assumptions, maybe the thing for you guys to know is that the assumptions that I'm making are just the standard assumptions that are used in measure theory. OK, so in the remaining 4 minutes, I just want to link up what I've said here to the hat puzzle. So what we've proved is that you can't take for granted that probabilities are well defined. So when you have a space and you know that a member of that space is going to be picked at random, you can't assume that there's a well-defined fact of the matter that what you pick is going to have a certain property. Sometimes there's a well-defined fact of the matter, as when you ask, what's the probability that a randomly picked point is going to fall between the 1/4 line and the 1/2 line. But sometimes they're not, as when you ask, what is the probability that the point you picked will be in the Vitali set. So this is my claim about what happens in the Vitali set. Sorry, in the hat puzzle. This is the question we really want answered. The question we really want answered is, before using the strategy, I could do no better than 1/2 in guessing the number of my own hat. That was the best probability of guessing correctly that I could aspire to. What we want to know is, what is the probability that I will guess correctly, given that I do use the strategy? That question is equivalent to the question of what is the proportion of possible representatives in the cell that I know to be actual that matches the actual color of my hat. And I claim that that is a non-measurable set. I claim that there is no good answer to what that probability is. So in the hat puzzle, it's not that the probability of guessing correctly has gone from 50 to something bigger than 50. What's happened is that it's gone from being well defined at 50% to no longer being well defined. And I mean, maybe you get some comfort from that fact. So we know that at least we're not like working in an inconsistent system. But there is something very disappointing about that. Because the thing about non-measurable sets, the things about probabilities that aren't well defined, is that we don't really have a theory behind them to explain how they work. So this answer to the hat problem is a little bit like saying, this falls into the hole in our theory. This falls into the questions that our theory is ill-equipped to answer. You know, at least we're clear about what those questions are, but it's not like we understand any better what's really going on in that case. Okay, so last question, Russ.
Is this the kind of hole? Is this like an area that maybe we could do some more math or think harder and fill in the hole, or do you think the hole is necessary?
That is an excellent question, and it's related to what Damien was asking. So there are certain constraints that most people think it would be nice for a measure theory, for a probability theory to satisfy. And what you can prove is that there's no way of satisfying them all. One thing one could try to do is work with measure theories that satisfy some, but not all. And the problem is that it's known that no matter which one you give up, you're going to get something weird. So there is the program of trying to work with one of these weird systems and see what you get. But I think it's partly just the program of like learning to live with weirdness, and not so much the mathematical program of you know, proving new results. I mean, there is a little bit of that, but I think it's mostly the form. Okay.